Okay, our second speaker today is Felipe Flores, so from the University of Virginia. Felipe is going to talk about on the symmetry of L1 of G for certain group extensions. Yes, please.
Thank you very much. So as usual, I would like to thank the organizers and for the invitation, for the chance to speak here, and for that very nice introduction. So I'm going to take you outside of the world of C-star algebras. I hope that's not too painful, but this is basically the property that I would like to attack. So suppose you have an inclusion, continuous inclusion of Banach algebras. And I would like to know when the spectrum with respect to this algebra is the same as the spectrum with respect to this algebra. So the question is the following. Okay. So this property has been studied a lot. It has like 6 different names in the literature. It's called inverse closeness. It's called spectral subalgebra, spectral invariance, smooth subalgebra, and so on. But I'm going to call this property spectral invariance. And I'm going to denote it by SI. Okay. And well, as the title says, I'm primarily interested in the case where A is a group algebra. So let me restrict the problem a little bit further. Suppose that A is a Banach star algebra. Let's say reduced. That only means that it injects into C-star algebra. And B will be the enveloping C-star algebra. Okay. So in this case, this question is better understood. And well, in this case, everything in the setup of the question depends on A. So we can give an answer in terms of A. So SI is equivalent to 2 different conditions on A. The first one, very natural, is that positive elements have positive spectrum. This is for all A. And the second one is also very natural. Self-adjoint elements have real spectrum. Okay. Or both of these are going to be called symmetry. A is symmetric. And I'm going to denote the class of symmetric algebras as just an S, because I don't want to write symmetry down every time. Okay. And if you notice, this is a very nice condition because we're just asking for basic spectral properties, right? And then we get that the spectrum is actually can be computed in a C-star algebra, where we can do all the spectral analysis we want, right? So the very basic question of this problem is when is the group algebra L1 symmetric? And before start giving some answers, let me pose some more questions just because. So we can ask the same question instead for L1. We can ask it for projective tensor products. That's another Banach algebra. Here A is going to be a C-star algebra. We can ask the same question for cross products type, cross products like C-star algebras. Algebras. So suppose that I have an action, a twist action of D on a C-star algebra, let's say. I get another Banach algebra, right? So I can ask the same question. And even further, I can just have a Feld bundle and form the algebra of integrable sections, right? So all of these questions have names. Well, this is the simplest one. When a group satisfies that this algebra is symmetric, let me write it like this. We say that the group is symmetric. When it satisfies this, we say that the group is rigidly symmetric. And we write it like this. Oh, here I mean that this algebra is symmetric for every A, right? Well, this one doesn't really has a name, but it's going to be important in the future. So that's why I wrote it here. But when every Feld bundle gives you a symmetric algebra, we say that the group is hypersymmetric.
I can't quite see, I
Yes.
can't quite see how many M's you're putting in the word.
Yeah, it's just because I'm going to write down symmetric.
It's got to be symmetric.
Yeah. Yeah, you're right. So let me start giving you some answers. Obviously, the question is an open problem, so I'm just going to give partial answers. But it's good to have examples, right? So some examples of symmetric groups are compactly generated polynomial growth groups. We can change the condition of compact generation for connectedness, and we still stay in the same class. Go same. What else? We have compact extensions of nilpotent groups. And we also have groups where every conjugacy class is relatively compact. So if you notice, all of these are, well, yeah, all of these are groups with polynomial growth. So it was a question if all symmetric groups were a polynomial growth, but that is not the case. Let me give you another example that's going to be important for this talk. So you can consider the affine group of the real numbers. Well, actually, yeah, was not the entire affine group. It's just the connected component of the identity, right? So this group is symmetric, but it's of exponential growth. Yeah, also let me mention that this is the first group that we know that is symmetric but not hypersymmetric. And that's going to become important in the end of the talk. All of these symmetric groups. So one of the biggest motivating questions of the problem is the following. Is the symmetry of a group the same as the rigid symmetry? And this is still open. but there is an example. Well, one can rephrase the same questions for any algebra pretty much, right? And there is an example of a C-star algebra such that, well, all C-star algebras are symmetric for obvious reasons. There's an example of a C-star algebra such that one can form the projective tensor product with another C-star algebra, and that's not a symmetric Banach-star algebra. So that question is just false in general, even for C-star algebras, but it's still open for group algebras. So that basically means that none of these are known examples. What I mean is that if we form tensor products with these kind of groups, we don't know what happens. That's what I mean. Yes. Yeah, so yeah. Maybe I didn't mention it, but like each one of these conditions is stronger than the previous one, right? Because every twisted action can be this algebra is a Feld bundle algebra. This algebra is one of these algebras with trivial action, and this is just this algebra taking A to be the complex space.
Did you say so that for those groups that you don't know whether or not they're RC, whether or not they're rigidly symmetric?
Yeah, we don't know. So
Are there any examples?
yeah, let me give you an example. That's a great question. Let me put it here. So any finite extension of a nilpotent group is going to be as good as we want. Okay. So yeah, you can take a Feld bundle over a nilpotent group, and you're going to get a symmetric algebra. So the purpose of this talk is basically to prove some permanence properties. So let me give you some. First one. If you have a semi-direct products with a compact group, this is going to be symmetric whenever the starting group was symmetric. Okay. Another one. If you have a central open subgroup of G, and such that the quotient is rigidly symmetric, then the group G was rigidly symmetric. Okay, both of these are by Lepkin and Pokunke.
So when they have symmetric product.
Yes.
Notation, which was the normal something?
G.
G, okay.
Yeah, so this is
What?
okay, cycle on G.
Yes.
K is compact. Sorry. Yes. K is compact. So basically, the goal of the talk is to prove some permanence properties that are going to be like these ones. But we're gonna revert the order, revert the roles of K and G here, and change central by compact, and that's kind of the main goal of the talk. So I'm gonna keep this one. Oh yeah, maybe it's also good to say that open subgroups and quotients of symmetric groups are symmetric. That's just kind of trivial, but it's good to have, I guess. Okay, so let me talk about the main tool that we're going to use. So as you can see, the property that I would like to investigate is kind of a qualitative property, right? But there is a stronger notion that is quantitative. So let me talk about it. Differentials of algebras. So back to the beginning, suppose that you have an inclusion of Banach algebras, continuous inclusion. We're gonna say that A is differential in B, or the inclusion is differential, if we have the following estimate on the norms. Okay. Before doing anything, let me give you some examples. So the first example is the class of Chadden P, no, the P class of Chadden operators inside of the compact operators on a Hilbert space. Right, this is just because it's an ideal, it's a norm ideal. Well, it's also Banach algebra, but you get what I mean.
What is SP?
The class of Chadden P operators.
Oh, okay.
What else?
I thought you were just saying CH.
CH.
Instead of SP.
Oh, sorry. Another example. Suppose, well, this example is more useful, but it's also stranger, I guess, if you have never seen it. If A is an H star algebra, then this inclusion is differential. Here, H star means A is a Hilbert space. Let's see. And the adjoint in A plays the role of the adjoint. I'm just gonna write it. You have this
Compact group, for instance.
yes, exactly. Thank you. So for instance, L2 of a compact group. Also the Hilbert-Smith operators. And I have a couple more of examples, but these are the main ones. Just to illustrate, another example could be, for instance, the continuously differentiable functions on an interval inside of the continuous functions. Just because this is basically like the Leibniz rule, right? Well, yeah, basically. well, you put norms on the Leibniz rule and you get this, in this case. What else? If you have L1 of a group, let me put it here. There's a way to construct weights on the group such that the weighted algebra is differential on L1. This is due to Ludwig, I think. Forgot the year. And if you want more generality than H-star algebras, you can do this with left Hilbert algebras, but that's just too much. So we have a lot of these examples. So what is this useful for? Well, this is useful for the next reason. If you have such an inclusion, and we assume that A is dense, then we basically have spectral invariance. Yeah. Actually, one of the reasons that this type of algebras are studied is because, as I mentioned, the spectral invariance is kind of a qualitative thing, but this also gives you some estimates on like the functional calculus. So maybe I should have said this before, but when you have an inequality of spectra, that means that you can compute the spectral calculus of A as elements in B. And this is going to end up in A anyways. And this allows you to get estimates on that holomorphic calculus. So let me give you an example, maybe. Oh, can I write here? Okay. So for instance, suppose that you're trying to compute the exponential of a convolution operator. Let's say that F is self-adjoint. So if you can see that this in the C-star algebra of a group, let's say, this norm is 1, right? But on the other hand, if you try to compute the norm on the L1 algebra, you don't have any good estimate. The only real estimate that you have is just terrible, right? Right. And what you can do with that, I don't know. But anyways, using this condition, people are able to get better estimations. So this condition is essentially stronger than spectral invariance. And I'm basically going to use it. It's so strong that whenever I pass to tensors, it's going to remain. Let me. Okay. Yes. I mean, holomorphic functional calculus. Because you can, I mean, this condition, suppose that your algebras are unital. So this condition translates to the inverses are the same. So not having these means that you can have possibly an inverse in one algebra, but not in the other one. No, because it might not be defined. Like this is like holomorphic function, like with the appropriate assumptions in the spectrum. Right?
The holomorphic function of the spectrum might not be a holomorphic function of the spectrum.
Yes, exactly. Yeah, I think so, yeah. Yeah, because you just play with the norms, right? Okay. Okay, so basically, the whole point of the paper was to use this, the thing that I'm about to show, in the case of L2 of a compact group. So that's how I'm going to derive the permanence properties I want. So let me tell you what a twisted action is. I mean, you probably know, but just to have a fixed notation. So a twisted action is just a for tuple where these two are maps that resemble an action, but not quite exactly. It's a cocycle type of condition. This goes to the homomorphisms of A. This goes to the unitary multipliers of A. I assume that these maps are Fourier measurable. And some conditions. So basically the conditions that you expect. This is a cocycle type of condition that I always forget. So also alpha kind of resembles an action, but twisted by a cocycle, by this cocycle. So if we have a cocycle, everything is nice. And the cocycle is trivial whenever I evaluate it on the identity elements. E is the identity element. Okay, and this is all quantified like x, a, x, y, z in the group and a in A. Okay. So whenever I have this, I can form an algebra in the way that you probably know it. This is a Banach-Star algebra. These are the Wagner measurable functions, which are integrable. Okay. And the convolution is the usual. Okay, sorry, that's a lot. So as I mentioned, the idea is to use differentials of algebras to understand when those type of algebras are symmetric. So the naive idea would be to just decompose an extension like that. So whenever I have a group extension, I think that this is 5. Under my assumptions, there is a section of this map. And using this section, I can build a cocycle like that. And basically decompose the full algebra of the group as twisted action algebra. Okay. So what do I notice next? Well, I notice that whenever I have a differential inclusion, basically I can replicate what happened. Oh, I think I already stood. Oh, here. Basically, under those assumptions, I get spectral invariance. So differential dense, and I'm gonna assume that this is a twisted action that leaves B, sorry, on B, that leaves A invariance. A is stable by the action. And then I get that the L1 algebras have a differential dense inclusion. Okay. So because of the property, I get spectral invariance. Now it looks like I could just apply this here, right? The only problem is that L1 is almost never a differential subalgebra of C-star algebra, let's say. Actually, I forgot the reference, but there is a theorem saying that for abelian groups that never happens. And yeah, if it doesn't happen for the abelian group, for abelian groups, we're basically hopeless. But I don't really need L1 to be a differential subalgebra. I can apply my results to L2. So whenever I have, I'm going to assume that K, the normal subgroup, it's compact. Okay. So inside of L1, I have LP, right? And because of the Holder inequality, these LPs are Banach algebras. In particular, L2 is a differential subalgebra of L1. But also this is a differential subalgebra of the group C-star algebra. This is because of the Holder inequality, and this is because this is one of the examples I mentioned, the Hilbert algebra. So I can apply my results to this algebra. So proposition, let me see how I code it. Okay, let's just mention the main result of the paper. So suppose that I'm gonna consider only this case. So when I write alpha and omega, I mean these ones, the ones that I get from an extension of groups. So under those circumstances, I have this theorem. This algebra. Okay. If this algebra is symmetric, then I can reduce the symmetry of G. And why is this an improvement? Well, basically because what I mentioned at the beginning, the algebras that have a C-star algebra, I think I erased it. Okay, so these two algebras are very close in nature, right? They both decompose as, well, something like this. The only problem is that in this case, here I get L1, and this is a better behaved algebra in general, just because I have a C-star algebra part. And those are, I don't know, there's more study about these algebras, so I can import results from other people. We have time for the, probably not. Okay. Well, anyways, the proof goes like this. L2 is a differential subalgebra here and here. So by the proposition, I get that if I put L2 here, it's differential and then it's here, but also here. And then this algebra is also a dense ideal here. And symmetry passes from dense ideals to the full algebra. So that's the proof. So the main point was that I don't really need the full force of differential subalgebras. I only need like a dense ideal that is a differential subalgebra. And let me mention a little improvement. Yeah, I don't want to erase this part. So L1 can be written like that. And that proposition is basically telling me that I can replace the second L1 for a C-star algebra, right? But they're actually equivalent. So let me mention a corollary. The algebra that I introduced there with the C-star part is symmetric, if and only if that algebra is symmetric, but not only that algebra, also I can replace L1 by LP for any P. And well, the best case is just P equal 1, that I recovered the original L1 algebra, right? And just to end the talk, let me mention a little improvement. So all of this was for general. Sorry, before the improvement, let me just mention that this gives me a permanence property. Why? Because if alpha and omega are continuous, and H is, let's say, hypersymmetric, then that algebra has to be symmetric, right? So this says that whenever I have an extension of a compact normal subgroup by a hypersymmetric group, then the result is symmetric. Also, if you look at this, that is basically the same result because, well, instead of central, I have a compact. Well, it's a little bit stronger actually because I don't need openness. But in the case that my subgroup is open, then the quotient is discrete, right? And for discrete groups, being rigidly symmetric is the same as being hypersymmetric. So I basically recovered this permanence property almost, but it's also still more general than this. And what else? Oh, yeah. So let me just mention that the case for splitting extensions is better. We actually get a characterization. So supposing that the extension splits, just basically means that this is an homomorphism. Suppose because this was the section of the projection, right? Then the symmetry of the quotient implies the symmetry of the full group. And actually, this is an if and only if, just because well, quotients of symmetric groups are symmetric. So yeah, in this case, basically what I have is that the, let's say, is quote unquote semi-direct products. And I well, if H, so this is only a semi-direct product as an algebraic group, right? Because the section might not be continuous. But anyways, it includes the case of semi-direct products. So in that case, I also get this, right? Just interchanging the roles of G and K, right? It's exactly the same. And also, just to conclude, okay. So I mentioned that there is a symmetric but not hypersymmetric group, right? I think I erased it. Anyways, so if I put that group here, the extension is going to be symmetric. However, I cannot put that group in the previous theorem I had there because I don't know if that's going to be symmetric. So I know that whenever that group acts on compact groups, that gives me an symmetric group, but I don't know about general extensions. And I think that's it. That's all. Yes.
So is there no example of a semi-direct product, let's say, of two symmetric groups with not symmetric? Either consonant, for example, and not hypersymmetric and then.
No, I don't think there is one, but it's, yeah, I don't think there is one. But there, we don't have any evidence actually, because like, well, we do know that whenever one of the groups is compact, we have these results, right? But even for direct products, like we only know that this is a symmetric group whenever this is symmetric and this is abelian. So it's super open. Yeah.
You mentioned he discovered a very important phenomenon. Maybe not too much to do with what we've been talking about. A very important phenomenon is a very large class of trees go down to the region of local contact. It's a very large class, including all the extra. If you look at the group C12, you look at the primitive courses, just, uh, contain the, classifiable, simple sequel, and non-beautiful Flores, in fact, some generalized non-beautiful Flores. Usually inductive limit is things that seem over and quicker. Kind of like some of the. Well, but that, I think that's absolutely major discovery in that life.
Yeah, I wasn't.
Okay, but you can look it up.
Thank you.
Cool. That's my, what I remember about, especially what I remember about. Right?
What else that results in,
Well, it's a universal phenomenon, and we discovered it a long, long time ago. And there will be very, very special cases where, like, if you look at the, Heisenberg, the three Heisenberg group, then it's, with discriminant forces, and they are, irrational people. So, or just,
For your result of here. Am I right in understanding that, I mean, generally, we want to have you look at algebras with respect to what is a differential subalgebra. Am I right in understanding that as long as you want to stick to group convolution algebras, it's going to be difficult to continue seeing as you're using this break, this is like L2 of K, which is a H star algebra, I guess, if and only if it's compact.
Yeah, it's not even an algebra if K is not compact.
Right, exactly. So is there any chance of like possibly enlarging this being a similar thing, or is this like is it as far as we can go?
So using specifically L2, I think is just this. Just because even in the case where you're looking at, for instance, so suppose you would like to attack this same problem, but with rigidly symmetric groups. So you would look at something like this. Let's say L2 of K with a C-star algebra as coefficients here, right? This is a Banach algebra, but it's not even a differential subalgebra like the minimal tensor product. Like the C-star algebra completion is this one, right? But yeah, you don't even have the differential condition, just because the C-star algebra typically acts on the Hilbert module, which is on this Hilbert module, right? I need different notation, but this is typically a different space, right? So you cannot do the same trick I did for Hilbert algebras. For Hilbert algebras, you have this basically. Right? Because you can represent the algebra as operators on itself. And that's a C-star algebra because itself was a Hilbert space. Right? And you can no longer play this game with these sort of things. So yeah, I don't see much future.